We are continuing our discussion of shear stress in beams. So in the last video we looked at the formula FV equals VQ over IB. And what this allows us to do, if we look at a cross-section, I'm just going to draw a rectangular cross-section. This allows us to find the shear stress at any point, right in the middle, maybe a little bit above that, or a little bit above that, or any point along the height of this beam, anywhere from the bottom all the way up to the top. We can calculate the shear stress. But at the conclusion of the last video, we found that the profile for the shear, if we calculated it at multiple points, would look something like this. At the neutral axis, which for a rectangle is just at its midplane, that's where we see the maximum shear stress. And that's typically all we're concerned about, the maximum. We don't care what the shear stress is up here, for instance, because it's a relatively small amount compared to this one at the midplane. That's where the maximum is occurring, so that's what we're concerned about. So although this formula here allows us to find shear at any point, we generally don't need to know that. What we do need to know is what is the maximum shear. Now, we're going to look at a couple different formulas to use for a couple commonly used shapes. We're going to be dealing quite a bit with wide flange steel shapes. We're going to be dealing with rectangular shapes, and we may occasionally even look at a round or circular cross-section. So when we are dealing with a wide flange section, the majority of the shear is actually resisted by this tall, slender rectangle going right down the middle. This is called the web of a wide flange beam, and these parts that stick out at the top and the bottom are called the flanges. The flanges don't really do a whole lot in terms of resisting shear. The majority of the shear stress resistance is accomplished by the web itself. And so we can basically simplify a wide flange by sort of ignoring the flanges, pretending like they're not even there, and instead looking at the area of that web. So in this case, the shear stress in the beam is equal to the shear force divided by dTW, where this is the V is the shear force, D is the depth of the beam from top to bottom, that's D, and T sub W is the thickness of the web, that is the T sub W. So basically we're just finding the force divided by area. The area in this case is the area of the web. So this is the formula that we will use for shear stress in a wide flange beam. When we are dealing with rectangles, we are going to use the formula FV equals 1.5 V over A, or this is also sometimes written as 3/2 V over A. Mathematically, this is the same thing. 3 divided by 2 is 1.5. So 3V over 2A, or 1.5 V over A. That gives us the maximum shear that is occurring at the neutral axis. And for a circular cross-section, we want to use FV equals 4V over 3A. Again, that's going to give us the maximum amount of shear that's occurring at midplane. So this is 4/3, this is 3/2, and this one is a little bit different because it's an approximation of the shear based on the majority of the shear being resisted by the web, V over dTW. So these are really the three formulas that you are going to be using going forward when we do beam analysis and we are evaluating the shear stress. So 3 separate formulas for 3 different shapes. Now, I don't believe we're going to have any cross sections that are different than one of these 3. If so, we probably would need to go back to this original formula up here and figure out what the stress is. But if we have one of these 1, 2, or 3 types of cross sections, a wide flange, a rectangle, or a circle, which is going to be all, if not most all, of the problems we deal with, then we'll be using one of these 3 formulas. So let's put one of these formulas into practice. If we look at example 1410B, we're given a wide flange section, a W16 by 100. It's subjected to a vertical shear force, so that's V, equals 80 kips. And we want to calculate the maximum horizontal shear stress using the average web shear approach. So that means using this formula right here. So our shear stress is going to equal V, which is 80 kips, or we could do 80,000 pounds, divided by, okay, we're going to have to look up the D, the depth of a W16 by 100. Information on wide flange sections can be found in Appendix A. Is for W shapes or wide flange shapes. And if we look up a W16 by 100, we'll see it has an overall depth of 16.97 inches. And the thickness of the web, T sub W, is 0.585 inches. And so when we divide 80,000 by the product of these two, we get 8, well, if we do it in pounds, we'll get 8,060 pounds per square inch, or PSI. If we'd kept this in kips, we would have gotten 8.06 KSI, or kips per square inch. So this is the maximum stress that will occur due to loading of the web. This is using the web shear approach.